So I think it's recording. Uh, Hello everyone. My name is Suraj Jaiswal and welcome to the third tutorial of the course Simulation of a Mechatronic Machine. So in today's tutorial, we will be modeling a spring mass system. Not one spring mass, but a two spring mass system. So as you can see in the figure, there is like two masses and two springs and they are making oscillation in the horizontal plane. We will be modeling something like this, but I'll show you in the next slide what can we expect or what we will be really modeling. So let's go ahead and these are the list of contents that I will cover in today's tutorial. So first I will brief you about what are the requirements as our normal drill. Then I will show you how we can model the systems using number of bodies, joints, springs, motion input to the system. And of course, we will be dividing our model into subsystems. So in the beginning, we will be modeling just one spring mass system, and then we will extend it to two spring mass system. So let's go ahead and see what are the requirements for the spring mass system that we intend to model. So if you see in the figure, uh, if you see in this figure, so this is what we intend to model. And by its very look, I can figure out, okay, there are at least three bodies. So this red one, green body, and blue body, and at least three joints. So the red one has some joint about with the with the gray body, and the blue one also has something with the gray body, and then there's a joint or it looks like a revolute joint, so that this green body is making some sort of rotation about the center of mass of this red body, and this is the motion input. And of course there are two springs, and we can also see this gray bodies are actually defined on the ground, and of course we can sense gravity. So we have a rough requirement of our system ready. So what we need a ground, of course. We need gravity, of course. In this system, it gravity may not be may not have like much effect because it will be sliding on the vertical plane. But as a good modeling practice, we will model it. Then we need an inertial reference system. So we need to model our system with respect to at least some origin, right? So that will be either you say inertial reference system or global coordinate system. Then there are three bodies. I can see red, green, and blue, and two optional bodies, which are these gray bodies. So basically, this gray bodies will this base plate and end plate will be modeled so that for better visualization we know what we are modeling instead of the spring is connecting somewhere without any visualization. And also this body red, we will say body 1, and then blue one we say body 2, and the green we say the rotating body. So instead of them sliding in thin air, it's better to have some base plate and end plate for reference purpose. And then we know we have three joints, two springs, one motion input. So we have our requirement ready. So it's good that we can go ahead and model the system. So first, let's go ahead and model the bodies. So let's go to my Matlab window. So I have Matlab version 2019A. It will take a while to open. So once it's open, make sure this folder is exactly the folder where you want to save your file. Then I will type smnew to open Simscape Multibody new file. It again takes a while because I think I work on the server, so maybe that's the reason it takes some time. So yes, we have our new Simscape multibody here. And we also have these basic components there, which is by default in every new file. So first good practice would be just go ahead and save the file as save as, and have it save it as you want. And then we will go ahead and first, okay, so this world frame already provide us with a ground and with a inertial reference system. So that is already taken care of. But we need to define gravity. So we need to double click this mechanism configuration. So by default in this software, the gravity is in minus z direction. But we want, if this is x, this is y, and z is coming out of the plane of the screen. So we want the gravity to be in the negative y direction, so vertically downward. So we'll change it from minus z to minus y direction. Then we press OK. So our gravity is okay. And we'll remove this components. We don't want it at the moment. So let's move it from the window so that you don't get confused. Then we have this solid component. So obviously we will be needing this solid component block to model our bodies. So if we double click this, so first uh, modeling the base plate and the end plate are optional, but my advice to you would be to model it for better visualization. And its length, breadth and height is 2000 millimeter. So we are entering here at in meter. Then 0.05, so 50 millimeter is the breadth, and height is 0.03. So this is x, y, and z. Length is along the x, breadth is along the y, and depth is along the z. If we press enter and then press F5, the visualization window is updated. Now over here, you don't need to worry about the inertia properties and the graphics because inertia properties actually it will be connected to the ground, the space plate and uh, mm, the end plate using some rigid joint or some just rigidly. So its inertia properties doesn't really matter. What matters here is the frame, and you need to be very careful about it. So if you see by default, there is a frame port R already available, which is at the center of this body. Remember very carefully, this XYZ is oriented in such a way, but in our system that we are modeling, you remember, we are modeling things like this. So X, Y in this plane and Z is coming out of the plane of the screen. Okay. So first we need to define two frames here. One frame will be on top of this R, but on the upper surface, so that body one will be connected to that point, and the second frame will be uh, along this edge, because the end plate needs to be connected to this body along this edge. Correct. So let's go ahead and we will turn this visibility off. It will still appear here, but in the block, it once we update it, this R will vanish. So let's go to new frame. Let's rename it as top. Then based on geometric feature, select the surface and use selected feature. So centroid of plus Y surface, correct? If you follow my slides, it is exactly the same details are mentioned there. So we have a frame on the top. Then we need to define a new frame. We can say it as edge based on geometric feature. And then now we want this edge and use selected feature. So midpoint of plus X and plus Y curve. And we press save. So our frames are ready. Don't get confused when you press this isometric view. the body is oriented in a different way. Don't get confused. You always need to figure out this X, Y, and Z and how it is oriented in your visualization screen. Okay, once you have done that, press OK. Let's rename it as base plate, and using Control R, rotate this so that edge is on the right. And as I told you, as a good practice, I always try to shape my blocks accordingly, according to the physical system that I'm modeling, so that it's easy for me to follow. Then click again, search for the solid component block. Then let's rename it first as end plate. Then double click this. The dimension of the end plate is 50 millimeter, 200 millimeter, and 300 millimeter as the length, breadth, and height. So 50 millimeter, obviously I'm converting it in meter, 200 millimeter, and 300 millimeter. Okay. Again, we do not need to worry about the inertia properties for the end plate because it will be connected with uh, the ground rigidly. So if you press enter and F5, the figure is updated. Uh, you can keep the graphics as gray or black as it is, but now you need to be very careful about, we need to define frames, right? And if you see by default, this frame R will be there, but we won't be needing it. Press F5. What we need is, first of all, you need to have visualize carefully. So this body will be connected like this with the base plate, and base plate will be the bottom, and both of them needs to be connected along one edge. So first we need to have this edge defined so that the connection can be made along that edge. And we need also a midpoint in the center of this surface so that the spring can be attached to that point. One end of the spring can be attached to that point, and the other end can be attached to mass 1. So before modeling, the overall picture of your model needs to be very careful in your mind. Then only you can visualize and model it carefully. So let's go ahead and model an edge. Rename it as edge based on geometric feature. Select this edge, use selected feature, so midpoint of plus x's and minus y curve, and press save. Go ahead and have a new frame, which we can call it as a midpoint, and based on geometric feature, select this surface, use selected feature, so centroid of minus x surface, correct, and save it. The other properties can be as it is by default. So now you have this edge defined, midpoint defined, which is looking good. Uh, don't get confused if you press isometric view and it's oriented in a different way. As I told you before, you need to see how is X, Y, and Z uh, visualized in your screen. So once you have done that, press OK. Your end plate is kind of ready. Orient this using Control R. Okay, first I need to see. Okay, yeah. So we need to orient this way only so that this edge will be connected to this edge. Okay, and midpoint is here, which is well and good. So now let's go ahead and let's model body 1. So solid block, again we will rename it as body 1. We need to double click this. Okay, so what are the dimensions of, so we will be using the same brick option to model our bodies. It will be a cuboid whose sides are 200 millimeter. So 0.20, 0.20, press enter, F5. So my block is here. Now I want the inertia property to be based on point mass, and the mass can be 10 kilogram. Enter, F5. Once we do that, the inertia properties and dimensions are there. Let's say I want this color to be red in color. So this is RGB combination. I increase the red value. Enter, F5. So I will exactly make the same color as I showed you in the first slide. So the red body, which I remember, we will call it body 1. And then we need to define frames here. Again, you have to be careful with defining frames in this modeling task. So by default, this frame R is already there. So we will be using it. So we'll keep it as it is. And this body will be oriented like this in the main system. So X, Y, and Z is coming out of the plane. So this body needs to have some reference frames. Clearly, one will be at the bottom surface so that it will be connected to the base plate. Then one will be on the right because it needs to be connected with the end plate using a spring. And then one needs to be defined on the left for future use, because at the moment we are just modeling one spring mass system, but we will extend it in the future using two spring mass system. So the other spring mass needs to be connected at the left end of this block, correct? So let's go ahead and model our frames. So first let's define the bottom frame based on geometric feature. Okay, first select the surface, use selected feature, centroid of minus y surface, and press save. Then again new frame, let's say suppose midpoint R based on geometric feature again, select this surface, use selected feature, so centroid of plus x surface, and press save. Then again new frame, this time it's midpoint left based on geometric feature, this surface, midpoint of this surface, use selected feature, so centroid of minus x surface, correct? Yes, and press save. So once we have defined all these frames, our body one is good to go. Don't get confused if you press isometric view and things look different. So press OK now. Let's reshape the block. Let's orient it so that this midpoint R is actually on the right. So like this. Yes. Okay. So once we have done that, we need to have one rotating body. So now, let's search for again solid component block. And if you want, you can also search it from the library browser. The reference is again in my previous tutorial. If I remember correctly, tutorial 1. So go ahead and watch that if you haven't. Let's say it's rotating body. Double click this. The dimensions this time are length is 40 millimeter, breadth is 300 millimeter, and height is 20 millimeter. So 0.04, 0.30, and then 0.02. Press enter F5. So this is my rotating body. Inertia, I want it again point based on point mass, and this time mass can be 0.5 kilograms. Press enter F5. Now let's say we make it green in color, because in our first slide it was shown in green color. So RGB, so I'll increase the green value. Enter F5. So now it's here. Now we need to define frames, and in this one there's a frame R by default, which is the center of this body. This body can be connected to the center of my body 1 from either of the end, whichever you like. So you can also define, if you want to connect it at this end, you can define a frame at the top. If you want it at the bottom, you can define a frame at the bottom. I want it on the top, on this surface. So let's go ahead. Top, based on geometric features, select this surface, use selected feature, correct? So centroid of plus y surface, and press save. Once we do that, it's okay. Oh, by the way, we did not turn this R off, so we'll turn this R off. We don't need it actually. Press F5 and then okay. So let's orient this so that this top needs to be connected to this R. Correct. Let's move this. Okay. So once we have it, we let's go back to the slides. So we have our bodies ready, which I showed you how to model them already. You can find the details in this slide. Now we need to define the joints. So before defining the joints, think carefully how many joints we required. We required 3 joints for the overall system, but right now we are not modeling the second body, so we'll not think about that body and that joint at the moment. So we need just 2 joints. One joint which will connect body 1 with the base plate. So for that we will use a prismatic joint or a translational joint. And then the other joint will be the joint that will connect body, rotating body with the body 1. Okay, so we can use Revolute Joint for the moment. So we already know the requirement for our 2 joints. So let's go back to our model. But before that, we want also this base plate to be connected to the global reference frame or the inertial reference frame. So you can simply, so on the top surface, the global reference frame is on the top surface of this base plate. If you see my schematic drawing of the system, you can simply uh, make this connection by dragging and connecting, right? But sometimes solver might give you some error. So for that reason, we use a weld joint. So weld joint, we search and we put this weld joint with default properties between this world frame and base plate. Okay, this is just for surety. I mean, uh, if if your solver is not giving any error, then this weld joint is not really needed. But if not, it's always to be good on the safe side. Similarly, you can simply connect these 2 edges, or you can use weld joint again between these 2 edges as you like. So it's just giving this base plate and end plate as there will not be any movement because they are the ground body basically. Excuse me. So now you need to define a prismatic joint. So let's search for prismatic joint for joint 1. Let's rename it as joint 1 and it's a prismatic joint. Correct? Now we will use the default properties of this prismatic joint, but be very careful that as I told you in my previous tutorial, that the revolute joint revolves around the z-axis. So if this is x, this is y, and this is the z is coming out of the plane, the revolute joint revolves like this. Okay. Similarly, the prismatic joint translates about the z-axis. So if z-axis is out of the plane, the revolute joint will move in such a way that it's coming out of the plane, going into the plane, or in this direction at least. Correct? So this is how the prismatic joint slides about the z-axis. But we want the sliding of body 1 with respect to this base plate in the horizontal direction, which is our x direction. So in order to have this transformation of axis, we are going to use rigid transform, or you can use the rigid transform which is already here. So let's use it. Let's remove this one. So we will use this rigid transform, and let's say it's rigid transform 1. Correct? So before that, we need to do some modifications in this rigid transform. So see carefully that the base frame will be connected with the base plate, and the Y frame will be connected, the follower frame will be connected to the prismatic joint, joint 1. So open this by double clicking. So the rotation method, we will use aligned axis, and there are 2 pairs. If you have followed the previous tutorial, you already know how we do this transformation. So pair 1, any movement of in the follower frame, any movement in the z direction of the follower frame, we want that to be transformed to the x direction of the base frame. So follower is connected to prismatic, correct? So any movement of the follower frame in the y in the z direction will cause a movement of the base frame in the x direction. And for pair 2, movement of follower in y direction can be movement of base in y direction. So no worries. And we press OK. So now this rigid transform is good to go. But remember, this joint is also connected to body 1. So we need to use another rigid transform. So you can just select, control, and drag. And it becomes rigid transform 2. Just orient this because the follower needs to be connected to joint, the prismatic joint, and the base needs to be connected with either the base plate or the body 1. So you don't need to change any properties anymore if you just reorient in such a way that the follower is connected to joint 1 and the base is connected to body 1 for rigid transform 2. Now go ahead and simply make the connections. So let's say we go ahead and make the connection, and this needs to be connected to the bottom surface, correct? Just be very careful in how you are managing all the blocks in your file, because sometimes it becomes very clumsy. So be very careful with that. So once we have done that, I would actually like to see if I have done the modeling correctly. So what am I expecting? I'm expecting a horizontal base plate and an end plate, and then body 1 will be just on top at the moment because that's what we have defined. So let's go ahead. The moment we run click, it will compile and the Mechanics Explorer window will appear. In order to view this, you need to have Y up, X, Y front, and then you need to press the front view. So if you see the animation again, actually there is no movement because there is no actuation to any body or anything. We're just defining the bodies, and that's how we we define. I always like to have this visibility of frames so that we know which frame is where. And you see, we define base plate like this and end plate like this, connecting along this edge, and then body one like this. So everything is fine, I think. So let's go back to our model. So once we have defined joint 1, we need to define joint 2, which will connect this rotating body. I have reshaped it as it should be connected. I mean, the way it is shaped in the system actually. And it needs to be connected with body, with the center of body 1. So basically port R using a Revolute joint. So let's go ahead and search for a Revolute joint. Let's rename it as joint 2 and Revolute joint. Correct. We can use the default properties of Revolute joint, but if you remember correctly from the first slide, we need to provide some motion to this joint or to the rotating body. So if we double click the Revolute joint, we go to the actuation. We want to have motion provided by input and torque automatically computed. Okay. If you want this body to be oriented in some certain way, you can give it using state target position, specific position target, but it's not really necessary here. So we won't be doing that. But if you want, you can give it here. And we press OK. So by default, this input position port will be appearing. So now what we have to do is just we need to connect this frame, and then the rotating body is connected at the center of body 1. Okay. So now if you simulate it again and go to the visualization window, you see we have rotating body as well, which is connected at the center, and it is oriented like this because we defined it to be connected on the top. If we would have defined it to be connected at the bottom, the entire thing would be up like uh, in this way, so that it is still connected at the bottom of body 1, but this rotating body would be on top. So it is how we have defined it. So once we have done that, it's time for us to model a spring component. So for that, you can either go to library browser and search for Simscape Multibody forces and torque and the spring and damper force. But if you don't want to do that, easy way of doing is simply search for spring and damper force. Let's rename it as spring 1, spring and damper force. And obviously we need to tune the parameters. So we need to have the natural length, spring stiffness, damping coefficient, and sensing force on or off. So obviously we are not defining damping as not like a spring damper system, but just a spring mass system. So damping will be 0. About the natural length, if you see the animation carefully, this animation, okay. So if you see this animation carefully, first of all, this natural length actually needs to be the distance between the connecting points, the exact distance. So the distance will be between this point and this point. What is the distance between these 2 points? You know the distance of from the center of this base plate to the edge, and then you need to subtract the width of this end plate. So it's like you need to subtract the width of this end plate, and you need to subtract the half the length or breadth of this body one. So then you'll have the distance between the 2 points. Also, be very sure that when you are connecting a spring, it should be aligned like this in a straight line, linearly, not uh, at an angle, not at all. It has to be in a straight line. How we assured that? We defined our body one and end plate in such a way that these 2 points are actually in a straight line. Okay, because the spring is linearly connected between the connecting two connecting points. And one more thing, that once we define the spring, there will be no visualization in our Mechanics Explorer, because there is no visualization for the spring component, but we know it's there, so no worries about it. So this length will be, so either you can calculate the length and put the value here. I think it will be 0.85 if I remember correctly. If you're not sure, let's calculate it here. So we knew the half of the length of base plate is 1 meter. Then the width of the end plate is 0.05, 50 millimeter. And then we need to subtract half the length or the breadth of body one, which is 100 millimeter, I think. So it comes out to be 0.85, yes. And then spring stiffness can be, for example, 1000 Newton meter. And of course, we want to sense force. And we press OK. So this force sensing port appears. So let me make some space. So this needs to be connected to this, and midpoint R needs to be connected to the spring. Okay. So we already have the spring modeled, but in the visualization, it will not appear. So no point going and seeing the visualization right now. Let's provide a motion input to this joint too, or the rotating body. Okay. So we need to give a position input, which is in radian, and we want it to be a constant motion. So let's give the motion input to be in radian per second. So basically we will be providing a constant a- angular velocity input. Okay. But before that, let's move on to our slide and see if we have covered all the things. So of course we have covered this, how we can model the joint, how we can model the spring, and right now we are modeling the motion input to the system, correct? Let's go back to the model. So yes, so we need to define the motion input in the form of constant angular velocity input. Okay. For that, if you followed my previous tutorial, I think tutorial 2, we have used ramp function to do that. So ramp function, and if you double click this, we need to give a slope, start time, and initial output. So start time can be 0, and initial output will needs to be the same as the initial position condition. Since we did not give any initial position condition to join 2, so it can be 0. But if you would have given set a state, target, position level, something, then the same needs to be reflected here. But it doesn't really matter, so it can be 0. It's okay. Now we need to define the slope, which is the angular velocity. omega. We want this rotating block to rotate at the natural frequency of this spring mass system. So what is the natural frequency of the spring mass system? So we have one mass of one body of mass m, which is 10 kilogram, and then we have a spring which is connecting that mass with the end plate, and the stiffness was 1000 Newton per meter. So what will be the natural frequency in radian per second for that one spring mass system? It will be square root of 1000 divided by 10. So basically 10 radian per second. So exactly we need to provide a motion input of 10 radian per second. So basically slope is 10 and we press OK. If for now you connect this port with this port, it won't connect because the signals are not compatible with each other. And if you follow the first tutorial, I have told you if the signals are not compatible, they will never connect. So for that, you need a Simulink. This ramp function is basically a Simulink input, basically a Simulink signal, and we have a physical system over here. So we need to convert Simulink signal into physical signal. How we can do that? By using this PS Simulink converter. So let's use this converter. And of course, if you double click this, and again the references from my previous tutorial, you need to tune the PS Simulink converter in such a way that you so we have an input function and you want the solver to know what are the derivatives of those functions, so that when Jacobians are calculated for the multibody system, they know uh, what will be the Jacobian and all. So we want the filtering and derivative as filter input and derivative calculated. Order can be second order, which means velocity and acceleration, and time constant can be 1 millisecond. And you need to press OK. So once you do that, I think we are good to go, and we can simply connect this RAM to this converter and then to the joint. So we have given a constant angular acceleration of 10 radian per second, and the sign does not matter because you'll see that in a while. Now if you run the simulation, let's see how is the visualization. Okay, we want to see it from the beginning. So let's go ahead. And now I also want to see how is the center of mass. So I just want the visibility of center of mass. So by pressing this, toggle visibility of center of mass of rigidly connected components. And now if I simulate, so this rotating body is rotating at a constant angular acceleration, and as a result of which it is causing the red body, which is body 1, to have a movement, whereas the spring is also making an effect, all of which is resulting is in an oscillation of body 1. And not just oscillation, if you see carefully, the amplitude of oscillation to and from motion is increasing. So we can see that in the animation. But we are also interested in seeing that them in plots, because that's the more scientific way of doing things. How you can do that? Okay, so first let's see how is the spring and spring force for spring 1. We can use this PS Simulink converter and scope to plot the result. So we will bring them over here so that everything is in one window. Okay, so let's rename it. So let's say it is spring force 1, and it is PS signaling converter. And let's say we are renaming the scope as spring force, correct? Okay. So now if we simply connect this port with this converter, it should be fine. But now at the same time, I am also interested to see the position and velocity of body one. So there are two ways of doing it. Either we can sense the position and velocity of this joint one, prismatic joint. If you double click this, go to this sensing position and velocity, it should be fine. But let's do it by using this transform sensor. I think in my first tutorial, I taught how to use this transform sensor. Maybe first or second, you have to check. So transform sensor, let's rename it as transform sensor 1. What we want to transform is we want to actually see the translational, basically the position in the x direction, which is the horizontal direction, and the velocity also in the x direction, and we press OK. So the position and velocity port will appear. Now let's have it here. I need to zoom out a little bit because everything is becoming clumsy so that I have more space. So now this transform sensor is there. Okay, so what we want to sense something with respect to something, right? So what will be the best reference other than the world reference frame? So for that, we connect the base of the transform sensor with the world reference frame. And then obviously the follower will be connected. You can connect it either to the center of body one or to the bottom of body one. Both will mean the same over here because we are just interested in position and velocity in the x direction, so the horizontal direction. So let's connect it to the center of body one. And of course we need this converter and scope. So if you select, press Ctrl and drag to sense the position and velocity from this transformer sensor. Let's rename it as position B1, and then this is mass position. Copy it again for the velocity part, and we say it's velocity B1, and this is mass velocity. So once we have done that, just connect the position port with the position converter and the velocity port with the velocity converter. Correct. So once we have done that, I think it's good to go. We will just simulate the system again. And now we want, okay, before that, so we also want to log the signals. So in order to log the signals, you need to select the corresponding signal, press right click and log selected signal. So this sign will appear. Similarly for these two signals as well, right click, log selected signal, right? So now if you run the simulation again, so the animation will be the same as we already saw, but we were interested to see the plots. And also this data inspector appears because we have logged the signals. So we can compare that. But before that, let's see the mass position of body one. So you see, even from the visualization, we could realize it's oscillating. or it's having a to and fro motion with an increasing amplitude. Similar behavior can be seen for the velocity plot, of course. And even in the spring force plot, a similar behavior can be seen. So whatever we saw in the visualization window, exactly the same thing we can see here. So once once this is ready, uh, so we know our one spring mass system, which has a rotating mass moving at constant velocities, up and running. It's very important to see the analysis part. So if you go to analysis, Simscape, obviously you can see the variable viewer. You can see how are the variables we have defined in the system and how are their values. And also we can see, go to analysis, Simscape, statics viewer, and we can see how is this, how is our model basically. What I'm very much interested in this degree of freedom, mechanism degree of freedom or tree degree of freedom. You see it's two. So obviously we have two bodies, which is body one and rotating body. So it should be two, but actually no. For this rotating body, we provided a motion input to the system, correct? So I don't know why this software does not take that into account. But you have to be very careful that whenever you define a motion input, such as this ramp function, this is kind of an additional constraint you're providing to rotating body. So that additional constraint compensates the degree of freedom of that rotating body, right? So over here, the number of degrees of freedom should be 2 minus this input motion function that you have provided. So it should be 1. Just be careful about that. Otherwise, if this ramp function was not there, if there was no motion input, then this 2 was correct. But whenever you define a motion input to the system, you need to take uh, the corresponding degree of freedom away from this total degree of freedom. Okay. So once this is ready, let's go back to our slide and see if we are on the right track. So yes, we have covered this part. So I also showed you initially how will the model behave with the visualization. Then I showed you how we can actually plot the result and analyze the system. And these plots I already showed you, and this animation, which is the same as the previous one. So we have our system up and running. That's a good news. Now we need to simply go back to our model and extend this to have the other body and the other spring. How we can, so okay, what are the requirements now? We need one additional body, which is body 2, one additional joint, which is joint 3, and it will be a prismatic joint, and then one additional spring component, which will be spring 2. If we model these 3 components, uh, it's good to go. So either you can simply copy this body 1, but I would not recommend you because there are so many changes done. So let's define a new body, which is using solid component block. Rename it as body 2 and double click this. So now the shape will be again brick, and the length, and it's a cuboid. So its dimension are 100 millimeter each side. So 0.10, 0.10, and 0.10. Press enter F5. So the dimensions are updated. Now I want the inertia properties to be based on point mass, and this time the point mass can be 1 kilogram, which is fine. Then I want the graphics to be blue in color as in the schematic uh, drawing that I showed you in the beginning, it was blue in color. So let's increase the blue value, enter an F5. So now my block is blue in color and frames. Okay. So by default, this frame R, if you press this visibility of frame, it's already there, which is at the center of this cuboid. But just see this. This body will be oriented, it's will be attached to the main system in this way. And at the bottom there will be a base plate, and on the right there will be a spring which is connected to body 1. So over here we need to define one frame over here so that it can be connected to the base plate, and you need to define one frame on this surface. Where you need to define that, we have to think very carefully. So remember I told you the spring needs to be linear. It should not be at any angle. And the spring, the second spring will be connected onto the middle surface, onto the midpoint of the left surface of body 1. Okay, and the dimensions of body 1 are 200 millimeter each side. So if you connect that spring to the midpoint of this surface, it will be wrong, because then the spring will be oriented like this, like it will be at an angle, because the dimensions are different. So in order to spring to be linear, it needs to be connected onto this edge, because it is connected to the center of body 1. So whose uh, x direction, y direction is 100 millimeter from the base plate, and this block is 100 millimeter in length as well. So again, if we connect this at the midpoint of this edge, the y direction is also taken care of, the x direction is also taken care of, and the z is obviously taken care of, because it's a kind of a planar system, so that's fine. So let's go ahead and define first our bottom frame. So let's say we have this, renaming it as bottom. Based on geometric features, select this bottom surface, use selected feature. So centroid of minus y surface, and press enter. And then again new frame, not midpoint, edge actually. Edge, you can rename it as edge R. So the edge on the right top, based on geometric feature, and this edge, use selected feature. So midpoint of plus x and plus y curve, and save. So now you have your bottom frame, edge frame, and center frame ready. If you reorient, if you press the isometric view, don't get confused when you see a different view altogether. As I told you, just be very careful with these things. And you press OK. So now I want this to be oriented in such a way so that edge R is on the right side. So Control R. Okay. I need some space. So I'm just moving stuffs. Okay. Don't get confused. I'm just moving some of the components here and there. Okay, so this body 2 will be here. So once we have our body 2 ready, we need a joint, prismatic joint. We can simply copy this 3, select, either copy and paste or control and drag. So wait a minute. Okay, is it becoming too clumsy? Okay. Okay, fine. So now if we just simply connect this joint, okay, rename it first. So this is joint 3. So if now we simply connect this joint with the base plate and then this body, the location of this body will be the same as location of body 1, which is at the center of the base plate on the top of the on the top surface, center of the top surface. So in order to have it at a distance, you need to use this rigid transform 3 to give that offset. And how much will be that offset? So if you see the dimension of body 1 and then body 1 is rotating, as well as this rotating body is rotating about body 1 and body 1 is also oscillating. So body 2 should be uh, at least greater than 0.5 meter from body 1. Let's say, to be on safe side, 0.6 meter, so 600 millimeter away from body 1 and in the negative x direction. So how we can do that? Go to rigid transform, translation, method, Cartesian, and just an offset we are giving as minus 0.6. Okay, 0.6 meter and 0, 0. Y and Z are 0. We press OK. Now if we just connect space the with the base of this rigid transform 3 with the base plate and make these connections, and then connect the base of the rigid transform 4 with the bottom port of body 2, what do we expect? Okay, so let me move a bit. So what are we expecting? We still haven't modeled the spring component. So we are expecting body to be at a distance from body 1, whereas body 1 will keep oscillating at the moment. So let's go ahead and see the animation if we are right about this. So with every small changes, you need to see this visualization screen so that you know what you're modeling. So yes, body 2 is at a distance as we wanted it to be. So things are fine. And that distance 0.6 is basically the distance from the center point. So just a minute. If so, distance from this point or distance from this line or this point to this point is 0.6. Okay. Because in order to define the spring, we need the initial length of the spring, which should be the actual distance between the connecting point. So we need the actual distance between this point and this point. And also, if you see carefully, it will be in a straight line. So things are fine if we go ahead and define our spring 2 component. So we'll calculate distance between these 2 points as we did before. So 0.6 minus half the length of this body 1 and half the length of this body 2. So let's go ahead in our model, search for another spring and damper force. Let's rename it to spring 2. And double click this. So the natural length is 0.6 minus half the length of body 1 is 0.1. Half the length of body 2 is minus 0.05. So it comes out to be 0.45. Yes. And obviously we want to sense force and damping will be 0. What will be the stiffness matrix? Okay, this is important. So you remember that body, the natural frequency of body 1 is basically 10 radian per second, and exactly in that velocity the ram the rotate the this rotating body is also rotating, right? We want body 2 to have the same natural frequency as body 1. Okay, so for that, if we know this formula, omega is equal to square root of k by m, which I showed you a couple of minutes ago. So we know omega, which is the natural frequency in radian per second, to be 10 radian per second. And we know the mass of body to be 1 kilogram. So how much will be the stiffness? Stiffness will be 100 Newton per meter. Be very careful with these things. So once you press OK, so this block is ready and it will be between. Everything is getting complicated. Just a minute. I hope it's fine. Yeah. So we will connect this edge R with the base frame of spring 2 and the follower frame of spring 2 with midpoint L frame of body 1. Once we do that and run the simulation again. Now before seeing the simulation, what are we expecting? That body 2 will also make some oscillation because it's connected with the spring to body 1. So let's go ahead and see the animation. So if we run the animation, now you see body 2 is also oscillating. But have you seen a very peculiar behavior in our system? When we didn't, let's see it again. When we did not have any body 2, in that case, the body 1 was making oscillation, yes, but with a increasing amplitude. But now the amplitude of oscillation does not increase. Rather, it's oscillating a bit and then going back to its initial position. Whereas body 2 is taking all the oscillation. So let's see this thing in the plot. So let's go back to our model. So in order to plot, we need for the spring to force, we need another converter. So let's say we have spring force 2 converter and we connect this port of spring 2 with the port of spring with this converter, and you can have separate scope for the spring force 2 converter as well, or you can use the same scope to plot to see the result. In order to do that, you can go to this scope, right click, signal and port, number of input port, you can define 1 2 3 as you like. But the easy way of doing it is simply select the signal and drag it to the scope. If you want to select it to port 1 or 2 as you like, I am saying it, let's have port 2. Okay, and let's remove this library thing. Okay, if I zoom in, not everything is visible, right? Yeah, so let's zoom out a bit. So now I can see the spring force 1 and 2 in the same scope. Similarly, let's use another transform sensor. So control select in order to transform and converter as well. Okay, I don't really have much space, guys. You have to bear with me. I just want everything to be like large in size, so that's why I have zoomed in so much. If I zoom out, I will have a lot of space, but then it will be difficult for you to see. Okay, so let's rename it as position of body 2, this converter, and this is velocity of body 2 converter, and this is transformer 2. So again, base of transformer 2 will be connected to the world frame, and this F will be connected to either the bottom port or the port R of body 2. Let's have it port R of body 2. Okay. Okay, now let's connect the position port to the corresponding converter and velocity to the corresponding converter, and we will use the same scope for the position. So just track to the respective slope. Okay, so once we have defined this, I think we will be able to see the plot. So let's go ahead and run the simulation again. So if we go and see the animation, exactly the same thing we'll see. So body 1 is oscillating, body 2 is also oscillating, but body 1 is not oscillating that much, but whereas body 2 is taking all the oscillation instead of body 1. Let's see in the plot. So if you see the mass position, so this yellow is for body 1, which is port 1, and blue is for port 2. So you see body 1 is oscillating, but its amplitude is kind of dying out, or again coming back, dying out, whereas body 2 takes all the oscillation. Okay, a similar thing can be seen even in the velocity plot. So even in the velocity plot, a similar result can be seen. Whereas if you see the force plot, so obviously the force from spring 1 will be large because the mass of body 1 is large, whereas the mass of body 2 is kind of 1 kilogram, 1/10 of body 1. So obviously the spring force will be less in that context. But that's not we want to analyze. So if we let's go ahead and compare the plot using data inspector. So if we plot the position of body 1 of this simulation run with respect to when there was no extra mass 2 or body 2, yes, you see in the beginning, like when there was no extra body, it was kind of oscillating with higher amplitude, whereas the amplitude now simply died. So what can we analyze? What can we conclude for such a system? Uh, I can conclude it's very safe to say that the addition of body 2 made an effect such that it acts as a damping mass to the system. So basically, if we plot the position of body 2 as well, it dampens the oscillation of body 1 and it absorbs the oscillation, and whereas it's not of increasing nature, it's oscillate and dies out, oscillates and dies out, and also its mass is 1 kilogram, which is 1/10 of body 1, and also the spring coefficient is quite less than spring 1, correct? So it's safe to say that such a system uh, is kind of, it's acting as a dampener to the system. Now, as I told you, like whenever we do anything, it's very obvious to think how a layman can be benefited out of it, correct? So this is kind of an industrial example. Even in industry, if I remember it correctly, in acoustic mixture, yes, in acoustic mixture, they use the same principle. So if you have a body which is vibrating and they make whose mass and stiffness coefficient is too much, and it oscillates with a very high amplitude, in order to dampen that, they just add another kind of mass whose mass is too less than the initial one, and the spring coefficient is also less, than the initial one, and then it dampens out. So if you haven't seen that, just go ahead and search for acoustic mixture and how this kind of oscillation or vibration uh, properties are affected by using this additional mass block and stuff like that. So that's very important to analyze what you have done in the modeling. So once you have done that, the last step would be just to go to the analysis, Simscape, statics viewer, go to this number of mechanism degree of freedom. Now it's 3 and 3 minus this ramp 1, so it's 2. Why is it 2? So 2 is because 1 degree of freedom for body 1, the other degree of freedom for body 2. So the overall degree of freedom of this system is 2. So let's go back to our slide and let's see if I've missed anything. So we have covered this part. We have also showed you how to model spring 2 and plot the, the data and compare it, and what analysis we can draw from the system, and basically how it's useful uh, overall for the industry or for the society. So that's all from my end for this week's tutorial. If you have any question, please do contact me at my email address, or if you don't want to be such a long process, you can just leave a comment in this video, and I try to check the comment section often, but there are not many comments in the previous videos. So if you have any, you can choose any option and I will be there to help you. So thank you so much, and if you liked this video, mm, please follow the other videos as well, and have a good day. Thank you.